So earlier on, I was trying to solve this Minesweeper puzzle by Euler. I managed to get one solve out of like maybe 20 over attempts. And yeah, let me just step you through the code just in case you didn't catch the earlier part. So basically, this code for Minesweeper is just trying to find out which squares are safe to press using some logic. Okay, and press those squares first. And then once it runs out of safe squares to press, then it will try one of the random combinations of, or rather, it will just randomly click on another square. Of course, the random click on another square part can be improved. Okay, but basically the code is like this. So we do have one thing called like this is the get logic method. The get logic helper function basically just steps through the grid and checks where the unknown squares are. Okay, and then basically not itself means only the neighbors. So if let's say we already know it's not a mine, then we don't need to add this into the sum. Okay, so like the number of mines around the square, if we already know it's a mine, like this is a mark one, we can actually minus one and not add that particular element inside that. Okay, and if it's for certain that's it's not a mine, okay, to play means is those squares that should be played. Okay, then don't need to add it. Okay, so yeah, after that we just add in this to the query. So the query is like this: you have a few like x and y coordinates, and then like these two squares contain one mine. So it's like a plus b equals to 1, a plus b equals to 1, and so on. Like a plus b equals to 1, c plus d equals to 1, and so on. So subset is basically a helper function that just basically converts a list to a set and then use the is subset method. I mean, you can also use list comprehensions to do this, but this subset method basically just checks whether like one's list is a subset of the other. So it's like if we have like this square, there's one that signifies this square here, and then we have this tree here that signifies this, and this. Then this one that references this square will be a subset of this tree, and so we can actually like subsume it and we can delete away. So like if let's say this encodes a 1 for this square, so 3 will mean that this and this equals to 2 because we take away this. Yeah, so this is the idea of the subset simplification method. Okay, so this is the function. Okay, and then we also return the list of the remaining elements after removing one list from another. Okay, so this is the main program loop. We have a logic which basically tells us like all these combinations of squares equals to how many mines, all this combination of squares equals how many mines. To play means the list of squares that contain no mines, and we want to play that next. Not play means don't play those squares because they confirm have mines. So these are all the ones that are flagged inside here. Available cells is basically just a way to just keep track of which cells are still left, and then we basically do a random over them if we don't have any good moves to play. So the game loop, first one is just to basically take in the grid, and I pad it with dots, okay, just so that I can apply this function earlier here without doing any if conditional to check for boundary, um, like the boundaries. Yeah, so this is a common trick for computer programs that does with grid. You can pad it with some like throwaway value that doesn't affect how you calculate. Then you can essentially do the same function like this function here. You can essentially do the same function for all nodes or grids. Okay, so we have a new function here called, I mean a new list here called newly open. We just look through the input grid and then just check whether or not this particular cell is it in available cells. Okay, if it is in available cells, it means it's a new cell that basically has been opened, because previously in available cells are all those with question mark. So this cell is no longer in available cells. We can remove this, and then we can basically put like the newly open, we add this. Okay, this is important because all the newly open ones, right, will be used later on in the logic loop to remove particular logic. Like let's say if you have two over here, that is this one and this one, and then let's say you open like maybe this square here, then I can update like this plus this equals to 2. I don't have to do like this plus this equals to 2. So those newly open is like giving us new information that we can use to simplify our logic conditions that we use for Minesweeper. Okay, and then over here, no need to append the logic of a cell with no surrounding mines. It means that if the cell has no mines, there's no need to do the logic loop here. Okay, because if the cell has no mines, it means everything is 0 and everything around it will already be open anyway, so we can skip it. Okay, because we have the relevant logic from the boundary cells rather than this cell. Okay, then we basically get the logic, which is the helper function above, append it here. So next is basically to simplify our logic array. So I just look over 10 times, and basically whenever we look through the query logic, if the value is 0, that means this value here is 0. It means all the cells, if you have a plus b plus c plus d equals 0, it means that a, b, c, d are all equals 0, right? Yeah, because Minesweeper is a binary game. So hence, this means we just append this into the save cells. Okay, and then same thing, if let's say everything is a 1, like a plus b plus c equals to 3, okay, the length of your query is the same as your value, then all these are mine, so we can put them into not play. Okay, then basically for those cells that already have a 0 1, we look through all of the potential logic statement and remove them. Also, we remove those that are already open in the logic statements, and then after that we keep only those logic queries that have the query of at least one cell. Okay, so next is check whether it's a subset of the other. So we do some sorting, and basically we just check whether, like, we look through, check whether the first one and then the second one, we just take two of the sets, okay, and then two of the list, and then check whether one is a subset of the other. If one is a subset of the other, like this, like ABC and AB, we can then remove AB from ABC, and then we are left with C is 1. Okay, we don't need to have the information of AB is 1 because this is already stored in another set here. Okay, we basically simplify it. So we can do that, and then we keep only one. So the last part is if there's an element that to play it. Okay, if not, okay, we pop the available cells randomly, and then we just basically print out what needs to be played. Okay, so I was thinking about this. I was thinking about it just now. The last 2 hours, like why this wasn't like that strong an AI. I mean, just to let you see how this is with it. Let me just click the try again. I mean, it managed to solve this sometimes, okay, but not very often. So let's see. Like you see, this one it solved until 211. You can see that it opened most of the grid. This AI is really quite competent. But then towards the end, oh wait, I shouldn't go full screen. Okay, sorry, because y'all cannot see my full screen. So like towards the end, when he has exhausted like all the moves that it has, you can see that over here the to play, after it uses up all the available moves in to play, okay, then it will just like randomly guess a mine. So like over here, it has no idea, there's no certainty at all. So it means that we have to like make a guess, and yeah, and normally at this guess stage we get it wrong. Okay, so I'm thinking whether or not there could be a way to like do our logic things better, so that we like remove more subsets and stuff, because I realize sometimes you might still be able to like deplete more of it. Let's see. So like over here, 3 is 1 2 3. This is 3. Okay, which hints very strongly that this 3 here can be mines, or it can be here, 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 here. Okay, actually, in this case, basically this or this are mines, and this or this are mines. It cannot be both, and hence this one is definitely a mine. There's something like this. Yeah, I think my program cannot do such complicated logic, and I don't think there's a need to. But what I'm thinking of doing is very simple. We just basically combine steps 3 and step 4 together. So we do this. Okay, for I in range what? We basically keep only logic. This one we can put at the start. Actually, we can put it at the, yeah, maybe we keep it there. What I'm thinking of doing is like, okay, first we do a sort at the start. Okay, maybe we should sort this in the inner loop. So sort the logics list in ascending query length order. Okay, then after that we do this step 2 here. We do it here, and then we do the step 3 at the bottom. I think I'm combining these two steps so that when we remove like the singletons, then we remove the subsets. Then after you remove the subset, you might have singletons, right? Then you can remove the singletons again. So I'm thinking this might actually help it to it might perform better. And this is just my theory. I haven't tested it out yet. After that, we keep the logic queries. Yep. Okay. So this is the last part here is to just make sure that the logic queries are kept so that they don't have like any like null cases. In fact, actually, this you don't need to put it here because you're not likely to have null cases here. It's only here that needs to be done like that. And let's try this out and see how this works. Okay, I'm quite curious to see whether this actually works. So I just basically combine step 2, which is loop through, and step 3 in the same loop. Oh, see, instant work. Yes. Okay, so that was correct. So I could actually enumerate more, but maybe that's just luck. Actually, I did have one more thing I was thinking of implementing to make it like be able to converge better. This actually went quite far. Yeah, maybe that was just luck, which is making a smart and intelligent guess that could be done. Because now I already did this logic thing quite a number of times. I think 10 is more than enough. Yeah, I mean, it would be great if it worked, but you see, like over here, 1, 2, 3, this is half chance. Like over here, this is 3, this is half chance, half. Actually, when we end up with cases like this, it's a game of luck already because there's no way you can open up one and yeah, this is like half chance. So basically, there's no way. Okay, let's just try submitting this code and see whether we solve it. Okay, because Minesweeper is also a little bit of luck. Actually, it's quite a lot of luck. Okay, so it didn't work. Maybe I try about 5 times, then I implement the way to choose the cell better. Okay, it didn't work again. Try again. Need a bit of luck to solve this. Okay, it didn't work. It looks like I'm gonna reach my count of submissions soon. Let's hope that it works. Oh no. Okay, try one last time. I guess I'm just not that lucky because oh, it's soft. Yes. Okay, so it means that this is good enough already to solve. Okay. I think I can rate as loved it. Okay, so this is considered soft. Okay. But actually what I was thinking of doing over here is to actually also make a move selection where we can select cells that have the least probability of the mines. Okay. So what this means is that we can actually add in the number of the probability of a cell getting a mine, and then we just choose the cell that has the lowest probability. Okay, how are we going to do that? Basically, we can do it rather simply. So, um, okay, then we have the avail cells here, right? So we can also have another array that contains the logic. Okay, so let's put here step 3. Maybe I can put here step 4. Okay, step 4. Okay, if step 4 enumerates the list of logic to find out the probabilities. Okay, so what we'll do is like that, because we have avail cells, right? So we can do like for each in avail cells. Okay, so we do have a list of, okay, so we can just put like cell props. It's like that. So cell props each. So this is the baseline, okay? So this one I put here. I just code this out because I think this would actually help it a bit too. So have a baseline cell probability. So the baseline cell probability uh, for available cells, uh, baseline cell probability for mines for all available cells. So what we do is cell props each is basically going to be this. The number of available cells and the number of mines divided by the number of available cells. So the number of mines are 99 minus away the length of the not play, because length of not play will be the available cells. Sorry, will be the mine cells. So this will be the cell props for each of them. Okay, and then what we do is we will then look through all of the logics and update. Okay, and update the cell props. So for query value in logic, okay, for each inquiry, okay, cell props each, okay, will be equals to the minimum, okay, or actually rather it will be the maximum because we take the highest probability. It will be the maximum of the cell props each, okay, coupled with your value divided by the length of query. Okay, because like let's say your value is 1 and your length of query is 2, that means it's 0.5% chance. Then like over here, this one will be 0.5% chance and so on. So we can actually encode the probability of the cell having being a mine, and then we use the most highest probability to have a mine because that is the most updated information that we have from the particular area of the board. So we can do that, value divided by length query, like that. And then yeah, let's just print out the cell props just to see how it is. So yeah, this will basically give us the list of cell probabilities, and then we just want to answer online. Oh, some of them are not in available cells. 95 is here. Oh yeah, 95 is not. 95 is available. It's in logic, but it's not in available cells, which is weird. Okay. It is weird. We shouldn't be having this issue. All of them have the same probability, it seems. but it shouldn't be actually, because like this cell should be one third. Oh, but the random probability over there, yeah, makes this higher. Okay, I'm just curious why 95 is not in there in the available cells. Okay, but no issues. Okay, if let's say it's not in the available cells, okay, so what we can do is we can do a dot get each, okay, which basically it's a way to get a dictionary element, okay, and then if not it'll be zero. So Python dictionary get function. So if we use the get, it returns the value for the key if it's in the dictionary. If not, we will get a zero. Okay, so that's what we do. So we try this again. Okay, so later we just need to sort the list of cell probabilities and we pick the cell that has the least probability of it having a mine. Just wondering whether all the probabilities are the same, because they all look the same to me. 213, 213. There we have 0.6. So we won't pick those cells here that have higher than that. Yeah, we'll pick the cell that probably has a lower probability elsewhere. Okay, so what we'll do now is make the move selection. Okay, so what we'll do is we have the cell props here. Okay, so in the list of cell props, what we want to do is we want to select the one with the least probability. So we can make this a list, make the dictionary a list. Okay, dot sort. Okay, key equals to lambda x. Okay, so lambda x is this one, x1. Okay, and we want to sort it in the increasing sequence, so this will be fine. So my cell sorted cell props. Okay, let's just we don't print this, we just print the sorted cell props. Then what we'll do next is actually we don't need this anymore. Next play will be sorted cell. Oh, I know why some of them didn't. Because of this random move selection, it may have selected 95. It popped out the available cells. So the available cells here, um, did not get updated here. We did not update the newly open here because of that. So that is also an issue with the old code. Our newly open did not get updated because of this available cells, and because we popped it down here. So yeah, now we remove this, it should work better. So next play equals to sorted cell props dot pop 0. We just pop the first element, and then it'll be this. It'll be like that. Okay, like that. So we have a list like that. Okay, maybe we don't need the word sorted. We can just have cell props. Like that. We could just have like this. We have a list of cell props. We sort them by the probabilities. Let's print this out and then we see what gives. Okay, what gives, whether this works better. Okay, how long did it survive for? Timeouts. Okay, that's weird. Okay, how did the timeout happen? Try again. Is the sort something wrong with this? Timeout. Whoa, why? Cell props equals to list cell props. Is this the way to convert dictionary in Python? Yeah, I need to do this. Yeah, no, I can just always sort the dictionary. Yeah, that works too. So a list of dictionaries, and then how far did I survive? 102. Not too bad. Okay, so it appears that just like looping through this here is not the best way to do it. So what we could do is we could just remove all those things in the dictionary that have the cell props below the. Okay, how about this? Okay, we basically cell props dot values, right? Okay, let's have the min prop like that. Okay, and then what we'll do is, okay, we want to just select randomly. Okay, so to select will be this list. Okay, so for for query for key value in cell props, if value is the same as min prop, okay, what we'll do is we'll add this key. Okay, and then what we do is cell next play equals to select dot pop. Okay, random dot range length of to select. Okay, so this should pop out a random element from the one of the cells that has the minimum probabilities, right? Okay, then I give the range. Okay, randomly pop item from list item. Isn't it like that? Random dot range. To select dot pop random dot range length to select. Okay, maybe the issue is the min prop. Okay, let's see the min prop. Let's print it out. Print out the min prop and see this is. Okay, maybe we print out to select. Yeah, as suspected, there's nothing to select right now. So if let's say we have this situation, because at the start there's no probabilities at all, right? Or rather, actually at the start, my available cell should be everything. So we should actually still have something, right? Cell prop shouldn't be empty. I mean, my avail cells is not empty, right? At the start. Okay, so at the start we haven't gotten the grade yet, I guess. Mm, okay, so basically all you can do is like that. If to select is empty, okay, else next play random dot ran range length avail cells like that. Yeah. So if let's say we have an empty to select array, we just take from all our available cells that can be played. Okay, this at least helps to start it up. So yeah, now it's randomly selecting one, but yeah, I guess this one is can be helped. Yeah, I mean sometimes it's like that. It's stochastic. So at least we select cells with the least probability. I think this didn't really help much actually. Yeah, it might be the reason. It might be because um, it's just a very minor improvement. The main improvement was really the main logic loop of the game, which was refined by doing the iterations of removing the singletons as well as removing the subsets that we just keep iterating those. So yeah, okay, this solved it. Nice. Okay, so actually there's a bit of randomness involved, so you can see like towards the end. Okay, now we submit this. See whether is it like a more faster code to get 100%. Okay, so it failed. Try again. Okay, so it seems that choosing the lowest probability of mines isn't too much of an improvement. Okay, but at least I think this would help it to solve more cases. Yeah, that's the problem with Minesweeper. Minesweeper, the board itself, even with optimal play, you can still fail. That's the nature of the game of Minesweeper. So it's not exactly a very fair challenge for like checking like which AI is better. I mean, of course, the better AI would not fail that many test cases, but still, even with perfect play, it's very possible to lose quite a lot of times, and that's just the nature of the game. Okay, so I seem to have not been able to. Oh, I can't solve anymore. So let's just see the results. Actually, I solved this puzzle already, so we can see this. Where's my solve? I solved one of them just now, right? Yeah, there we go. 100%. Okay. So if we go to like my reports, okay, I kind of need to solve it to see other people's solutions. Okay. Yeah, I'm just seeing what are the people's comments for this. I actually quite like to see the other solutions. These are all yours. Okay. Got it at try 31 with the laziest AI. Success rates above 50% are possible. Okay, so oh wow, above 50% is possible. That means my AI is not exactly the most possible ones. Hmm, that's interesting. Success rates above 50% are possible. Hmm. Yeah, B has a mind. Share. The best algorithm should be a set solver. Yes, each slot is a boolean variable. Yeah, yeah, yeah. That's correct. That's that will be a. I'm also using something like set. I'm using some like boolean solver, but my boolean solver has is a very simplistic one. Yeah, nice. Yeah. So okay, let me try submitting again. I need to submit, and oh, I reached the max submissions in a row. Okay, but I've achieved the best score of 100%. I think I'm not sure whether I can view other people's solutions to this right now. Okay, so I've solved it. Okay, okay, but I cannot really see other people's solutions. Yeah, but I think this is not the optimal ones because the optimal code, as what Euler mentioned, you can solve a success rate of like at least 50%. Wow, that's impressive actually. But I'm happy in my code. I mean, it doesn't work all the time. Hey, what happened? Oh, this is just bad luck. Okay, appears to me like the like over here. Actually, I think we can get some information already, right? Like here's three. This is a two, but my solver still cannot differentiate between this like 1 1 and this is a 2 and this is 1 1. That means that like my 2 has this 2 here, my 1 2 3. Actually, we can get some information from this, but in order to do that, we need to consider more complex patterns, like where are all the possibilities, which will need how will I solve this? One cell here. I mean, we already know this 2 is 1, we know this 3 is 1, hence this is this should be 0. So actually we should already know that it's empty. Okay, indeed we do solve this too. So then the rest, like once we know this, so actually to play here should have something. Yeah, we do have. Okay, that's good. Okay, then once we reach here, we don't have any clue already. Is it true? Like here's 1, means that this 5 has 1, and then since this 5 has 1, okay, I think I need to do some overlap. So if this 5 has 1, it means that we can take a subset. This is 2. This should also have at most 1, and then hence this. Wait, 1 2 3 4 5. This 5 should have 1. The 1 should appear somewhere here. This is 3. So this will be difficult. This won't be a simple solution to solve. So I can understand why my program didn't work. Yeah, this one requires like a second order logic. You need to think like you need to guess some kind of um, you basically need to guess, look ahead a bit, and then like yeah, actually it's working pretty well. Okay, let's keep trying until we solve it. Okay, so this obviously is not the most optimal algorithm because it cannot solve this fully all the time, but at least it tries to minimize the amount of guesses it needs to make. I think that's no, not sorry, not guesses. It tries to minimize the amount of risk it takes by choosing the square that has the least probability of mines. I think that's good enough. Yeah, yeah. Not sure though. It looks like it's actually performing worse than my original algorithm when I didn't cater for the. Maybe it's just luck. I'm not sure, but yeah. Let's suppose We just go back to my base case like that. Let's suppose we just do this. We don't even do the action probabilities. Let's see what happens. I actually suspect that this action probabilities thing might be coded wrongly. Yeah. Okay, we try again. See, it solves this one. Yeah, it's actually solving quite a lot better now. Okay, so that was two success, one failure. Why though? I would say that choosing the cell with the least probability should be actually better. Did I add this function wrongly? Okay, so it might just be luck. I think I might have coded this wrongly. Like here, maybe I don't do a pop. I can just do like that. Okay, let's bring back the mean probabilities. Now this is interesting. When I try to optimize for the probabilities of cells, choose the least probabilities, it actually worked worse than before. See, now most of the cases fail. When the just now without considering all this, it worked better. So maybe sometimes it might be better to choose one cell that is higher probability. Oh, okay, now it works. Okay, well, I'm not sure what's the cause of why this might be better. I'll go and do some investigations later. But let's just enjoy the process of the AI solving this game. Oh, this took me 3 hours to solve. This is one of the toughest ones. So the idea was just to look through each of the possibilities based on this number here, and then basically if one is a subset of the other in terms of the unknown cells, we eliminate it. As you can see like this, ABC is 2, AB is 1, we get C is 1. Then the top part here will just be remove the singletons, like A is 1, then we can remove all the singletons from the existing logic, either 1 or 0. And if like the cells, the length of the number of variables here is the same as the value, like length 3 and the value is 3, that means each of them are mines. We can then put all this in the mine list. Okay, remove cells for certain. And if all of them are 0, you know all 0. Yeah, so this is the idea. Okay, let's appreciate how the AI solves Minesweeper. I'm actually very appreciative that the AI can actually play this, because I myself am not a very big fan of Minesweeper because there's some stochasticity in it. But yeah, at least the AI looks like it's playing pretty well. Okay, it's a little long. Let's just fast forward it. Blah, 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 blah. Okay, nice. I think that's also a little over 50% or so. Okay, so and that's a wrap. And yeah, thanks for watching the stream. And I hope you enjoyed this. Yeah, for more details, feel free to go over to my Twitch or my YouTube to check out the full video to see how I coded this. And yeah, thanks for watching and see ya. Bye.